Again, so in a previous video we discussed the standard basis vector notation, which can actually be helpful in seeing how to calculate the magnitude of a 3D vector, which is a quantity that is of prime importance for lots of different applications, such as the dot product or the vector projection, which end up being really important for a lot of other applications with multivariate calculus. So to find the magnitude in 2D, we simply used the Pythagorean theorem, and it was pretty simple. But as you can see now, the magnitude isn't simply the hypotenuse of a right triangle in 3D. It's a little more complex, but all we have to do is decompose this more difficult problem into some simpler ones, and we can find it pretty quick. And essentially what we're doing, we're taking a harder problem and we're solving it by breaking it down into easier problems that we have tools for and that are easier to solve. And this is essentially what all of mathematics does. It just takes difficult problems, say for example the area under a curve, and it breaks that down into a bunch of easy problems, a bunch of areas of rectangles. So this is just kind of another way that we do that. So breaking this down, we can first look at our I hat and j hat components, and these have a length of 1 in the x direction and 2 in the y direction. Now since these basis vectors are orthogonal, right, our x and our y are going to be orthogonal, there's going to be 90 degrees right angle between them, they form a right triangle, so we can find the hypotenuse as the square root of 1 squared plus 2 squared, just like we found it in the previous video. And now we're making some progress here, because you notice that this hypotenuse we just found would be orthogonal to our k component, since both our I hat and our j hat vectors are orthogonal to our k hat vector. Therefore we can use the Pythagorean theorem again to find this other hypotenuse, which is ultimately what we're looking for here, formed by these two triangle side lengths. So we can say that our magnitude of our vector, we'll use these straight brackets with our vector notation for a here, and that magnitude is going to be equal to the square root of our quantity of the square root of 1 squared plus 2 squared plus 3 squared, where 3 of course is the height of our in the z direction. So that when we're squaring that square root, that simplifies down, so we just end up with the square root of 1 squared plus 2 squared plus 3 squared, which is the square root of 1 plus 4 plus 9, which is the square root of 14. So that's our magnitude, and you can similarly show the more general equation for the magnitude of a vector A is just given as the square root of a1 squared plus a2 squared plus a3 squared. So that is the equation that you can use to find magnitude of a vector. And we see we found this formula pretty easily when we just break down a harder problem into some easier components, and it's not too bad. So this magnitude is obviously useful if you want to know the length of a vector, but as I mentioned, it lays the foundation for dot products and projections, which are key components to multivariable calculus. So in cases like this, we're often trying to find a unit vector form of a given vector. So for example, we'll call the unit vector of our a vector a hat, and this a hat, basically it's going to have the same exact direction as our a vector. It's just going to have a magnitude of 1. So it'll be the same direction, different magnitude. And to find this unit vector, all we have to do is simply divide our vector a by its magnitude. So we have our a hat vector is equal to our a vector divided by its magnitude, which is equal to these brackets of 1, 2, 3 divided by its magnitude, which is square root of 14. And just like we can multiply each component of a vector, if we want to divide, we can divide each component too. So this is going to be equal to brackets 1 over square root of 14, 2 over square root of 14, and 3 over square root of 14. And we can check to make sure this is a unit vector by finding its magnitude using that same method we just showed. So what we'd have here is the magnitude of a hat is going to be the square root of the quantity 1 over square root of 14 squared plus the quantity 2 over square root of 14 squared plus the quantity 3 over square root of 14 squared. And squaring all those components, we get the square root of 1/14 plus 4/14 plus 9/14, which is the square root of 14 over 14, which is just 1. So you can see that we did in fact confirm that we did find the unit vector pointed in the same direction as our vector A. Alright, so it's definitely good to know how to do these by hand, as we sort of showed here. But as these get more complicated and as they become parts of more complicated problems, it's going to be much easier to do this computationally. So in the next video, we'll show how to do some of these operations using MATLAB. So until then, take care.